Okay. 1 more minute, 2 more minutes, 2 more minutes. All right, let's get started. So let's see. Let's see if all my video stuff is recording properly on a day like that. Okay. Good enough. So, sorry for the last dropout. Technical problems. I have no idea what happened with the system here, but it got fixed now. Did you guys look at the lecture I recorded? I saw plenty of emails about problems with the simulator installation, and I'm going to fix that in the next 24 hours, everything, and we'll get going since you need this for the next homework assignment. So it was essentially to get going, and now we'll fix everything, and then you should be fine to actually use it, I hope. Anybody has any deep insights? Anything to complain? Anything to worry about? Everybody has should have some computer where this stuff runs. That's the hope in grand general. If not, then you need to let me know. We'll give you an account or somewhere on one of our computers for login. So that's also totally doable. How do we proceed? So I want to do in this week 2 more lectures, one on optimal control and one on common filtering. So the 2 topics are extremely closely related. And they're kind of important in robotics, since people use these frameworks a lot. I'm not going to dive into grand detail of optimal control. This would be way too much. The same way as not in grand detail of common filtering. But the topic, again, is something which people use again and again, since it's elegant, beautiful, and it works really well. So it's actually worthwhile knowing about. So I want to get this done this week, and then most likely starting with next week, try to focus as much as possible on preparing the project and getting you back in the lab to the robots and getting all the homeworks finished up so that by the end of the month we're done. For the final quiz, as I call it officially, you saw the date online. That's the last day of class. So we do this a little bit elegantly to avoid that we push that into the finals week. So that the reason I have to call it a final quiz is because then finals have to be in the finals week. A final quiz can be on my last lecture day. And this way you have done before all the other tests which you have to write start, which is more convenient. How this is going to work, I will shortly distribute a catalog of questions. And that's what you're supposed to study. You will get usually about 13, 14 questions out of this catalog. You will get no answers. I mentioned that before. And you will see 2 or 3 new questions. It's a closed book quiz in the end, about 14, 15, 16, 17 questions. Almost 85% you should have seen. You don't know the answers. You have catalogs of crazy people who try to provide answers on that. Never trust them, since there's bugs and stupid mistakes in these questions, which I've noticed. But it shouldn't be too hard. So you see exactly how questions look like. They're not that you solve math puzzles or something like that. They're more conceptual and general questions which test what you should know. And the material is going to be all what we've been doing in the lectures, background reading in the book, but the lectures, what we've been doing, your homework assignments, the project, these are the topics you should really know about. Okay, Usually not too bad. Good. So this topic today is actually, it's not very long and complicated, so we might be able to get this done quicker today. So optimal control. And the story what we want to get into is essentially, remember when we talked about splines at some point? There was a way to explain splines by basically saying they optimize something. Like a third over spline was actually optimizing a cost function, which was kind of J equals integral over x dot square dt from some time horizon 0 to tau. That's basically the length of the trajectory you want to do. Or, so this gave a cubic spline. In the same way, you can actually show that if you do, and I mentioned that before, if you take the third derivative to the same integral dt, that becomes the fifth order spline, which is also called the minimum jerk spline. I will actually try to push that into your homework assignment, that you try to derive that and make a robot, actually the real, the now simulator, do movements under a fifth order spline movement plan and see how well this works. Now, this basically sets up this generic framework like, what can we do with jigs? Can we derive controllers? Can we derive general principles of robotics from optimization? And people are very excited about that. This is really an ongoing field, has been ongoing for many, many, many years, and people like it. So optimal control is cool. The idea is you create a cost function, and you kind of develop controllers out of that, and they know that they're somehow optimal with respect to some criteria which you made up. Now, there's also a criticism towards optimal control. So basically, the optimal control world and kind of the quote-unquote standard control world are two different camps in robotics, if you want to. And the argument is always that a real control theoretician wants to have something which is really robust, where you can prove stability, where you can say this will work with probability 1. The optimal control people are different. They want to basically optimize the criteria and still have stability and all kinds of things, but they care primarily about the optimization criterion. And this argument which people often bring toward, which is against optimal control, is kind of nicely exemplified. I may have shown that before, I forgot. So if I create the Grand Canyon for you here, I think I used this example before. Get rid of this. And I give you a balancing beam to get across, or I give you a nice big suspension bridge to get across. Now, if I ask you, go over there with basically minimal time, minimal path length, you would take the balancing beam in optimal control. But the safe thing, of course, is to take the bridge, since you have much more space and you don't fall off. So optimal control frequently, when you do this in general, create solutions which are incredibly targeting some special parts of the world which can be exploited. And that may potentially be dangerous and not very robust. And that is essentially what people experience a lot in robotics when they work with optimal control. They have these great optimization criteria. Let's get something that get to a point, minimize some motor commands, for instance, minimize time to get there. And it works great in simulators. And the moment you put it on the real robot, which has modeling errors and some kind of sensor noise and other idiosyncrasies, it doesn't work at all anymore. So people are permanently going back and forth. I actually attended 2 weeks ago or 3 weeks ago, I forgot, a workshop in Florida where people were discussing how optimization methods work for balancing control for the big DRC Atlas robot from Boston Dynamics. Many of you may have seen it, that big, clunky, super, like whatever, 150 kilogram heavy robot. And they all applied some kind of optimal control techniques, but they had the hell of a time to make it work on the physical system. But in simulations, everything worked back here. So this is kind of the background behind that. What I want to do today is actually just go quickly into optimal control and talk for a moment about Bemann's principle of optimality and basically show you how to derive a very generic controller which people like a lot. And this is linear quadratic regulator control. And this is really a great controller. It works in linear systems. It also works in nonlinear systems if you can just do a local linearization. And it's an incredibly robust controller, so it doesn't really have that balancing beam property necessarily, which I'm describing here. And people use it in many different contexts. So it's actually worthwhile knowing how it's derived. It's actually very easy, as you will see, in what you can do with it. So let's see how this works. So how do we start with optimal control? So I do this all in discrete time right now, not in continuous time, since it's nicer in discrete time. If I do it in continuous time, I have to work with some partial differential equations, which is more annoying. So it's essentially, we start with a discrete time dynamical system, which is just xn plus 1 equals f of xn and un. You can always get that out of your continuous time system. You need to discretize it on a computer anyway, so it's not a particular big deal. And you have this very generic cost function. The cost function usually says it's so this is over a finite time horizon most of the time. You can also do infinite time horizons, but it's the finite time horizons that's mostly what we care about. So there's essentially, when you reach your final state, that is at time capital N, there might be some parameters, you get some reward or penalty file. This is basically says, it's essentially like you are reaching the goal and you get $1,000. If you don't reach the goal, you get nothing. So people like to have that terminal reward frequently as a special term. And it's special insofar it's not depending on the motor commands. That when you reach the goal, there's no motor command anymore, which can be taken into account. And the other component is just the sum over the entire trajectory from I equals 0 till n minus 1. That means the second to last time step. And you sum up some cost function, which may depend on your current state. I have to see how many indices are. Xi, Ui, some parameters alpha potentially, and that's essentially it. So it's actually a very straightforward problem to formalize. You just sum up cost terms along the trajectory. They depend on the state, they depend on the motor command, they may depend on some parameter settings you have. These parameters are kind of generic parameters. For instance, you could put in the gains of a PD controller into this optimization framework and says, I give you a penalty if you need to use high gains. But then you keep the gains constant over the entire horizon. You see they're not indexed by I. So these refer to parameters which are valid for the entire time horizon. These are terms which are just instantaneous at every time step. Okay. So, and what we want to do in the end, we want to find a sequence of motor commands, and basically this is like, people often write it U from M0 till, in our world, N minus 1. The sequence is just a vector of motor commands, which kind of optimizes this cost function. So that's the generic setup, not too complicated. Cool. How can you solve problems like that? You're all computer scientists? Are you computer scientists? Electrical engineers? Anybody not a computer scientist? Okay, you're excused. Who knows about Dijkstra's algorithm? Everybody? Everybody almost? Yeah. Okay, perfect. Dijkstra. Dijkstra is essentially based on that. Dijkstra is based on the idea that you basically try to find optimal solutions by some backward sweeping and basically finding the solution or the path which is kind of optimal. And this is kind of a simple example if you basically have some kind of a graph. Terribly drawing, sorry. Start here, go to the goal here. And you try to find the kind of path with the minimal cost or the maximal cost, depending on what you want to do. With minimum and maximum, we don't care. We just flip a sign. So how do you do that? Well, there are stupid ways how you can do that. You could just randomly try to enumerate every possible path. So that's really dumb to do. And a better way is simply to start, for instance, at the goal, and then basically sweep backward and basically look at where can you, which states can reach the goal, and what is the cost how to get there. So for instance, from here to there it's 1, from here to there it's 20. Then you have that. And then you basically take each of these nodes again and sweep backward again and see basically expand what's the cost on this guy. And we basically look always, okay, this is basically a cost 1, then here I have a cost 3, that's cheap, this here is a cost 15, that is expensive. So we quickly start getting a path which is basically cheaper
by 1 plus 3 plus 4 plus 7, and we get a cheap path. All the other paths are going to be more expensive. So by this backward sweeping, you can essentially find the cheapest path without enumerating everything. Very simple. So this has been formalized a long time ago, essentially, as Bellman's principle of optimality. And that is really what matters for us the most. And what Bellman basically wrote in his book at some point is an optimal sequence of controls in a multi-stage optimization problem. So multi-stage, we go over multiple time steps. As the property, whatever the initial stage, state, and controls are, the remaining controls must constitute an optimal sequence of decisions for the remaining problem. With stage and alpha resulting from previous controls type. So what does it mean? It essentially means wherever you are and you look around, so you get, when you do at this time step I, if you apply a control UI, that costs you some money. And you can basically see, okay, how much money does basically a particular action cost me? Where does it take me? So what is the state I plus 1? And what is going to be the total cost to get to the goal from here onwards? Okay? And the star denotes the optimal cost. So you assume at this moment that for every state, you already know the optimal cost to go. Okay? And simply you just look around and say, okay, I try action 1, cost me 5, action 2 cost me 10, action 3 cost me whatever, 20, but I do 5, and then the cost to go is just essentially 20. I do 10, and the cost to go is 1. Actually, then it turns out that doing a cost with 10 immediately and then having a final cost to go with 1 is much cheaper. So this kind of consistency, that basically the one-step reward plus what comes optimally afterwards, that these things together have to be optimal again, is really the essence of all kind of optimal control and optimization methods in control which we have. And the idea is basically that you have to find these kind of controls at every moment of time. So what is optimal in this regard? And you can see you always depend on the state to go. Okay? You need to know what is the cost to go. This is why this backward sweeping business is useful. Since, for instance, I can just start here at this goal. The cost to go is actually 0. That's great, no problem. So then I know the cost to go here. So now I can go to the next state and say, okay, if I'm here and I'm taking an action in this direction, it costs me 20 and the cost to go is 0. So I can actually compute what is optimal. What is the optimal cost for this state? Or I can go here and say, okay, if I'm here, I take an action in this direction, it is 1, the cost to go is 0. So that is a cheaper way to go. Now I know the cost to go, the optimal cost to go is from those points. And I sweep backwards. So I don't have to exhaustively enumerate everything. I just do this kind of cheap sweep backwards to figure out all the cost to goes. So the backward approach is really what makes this work. All right. So that's essentially it. So this here is called the Bellman equation. And there's also in continuous time, it's called, there is something which is called the Hamilton-Jacobi-Bellman equation, where you get some partial derivatives. I show you this at the end in the last slide. But again, the discrete time version is much easier. And we'll see in a second actually how we can use that. It looks a little bit abstract to start going with. It will turn out that this is very trivial to apply. So let's look at some cost functions. And there's different cost functions people have been using a lot, and you can make up any cost function you want in the end. One cost function which people like is what is called a bang-bang or minimum time control. Let's assume we want to minimize things, okay? So basically, get every cost you incur is like a penalty. You pay something. So if you simply say at every time step, what if you take, you pay 1, and also it can be 100. It doesn't matter. The scaling of cost function doesn't matter in general. Then all what you're going to do, if you want to minimize that, you want to take the minimum number of time steps to get to the goal. Then in the goal, when you're absorbed, you're not paying anymore. All right. Actually, this is called bang-bang control. It has some interesting properties, and it's actually very useful to know about that. So, okay, here comes your optimal control problem of the day. You all can relate to that. Here is a racetrack, okay? This here is the goal. And here's the start. And you're driving a fine car. Porsche. I'm German, okay? Some loyalty. There you go. Now, you start here, and you want to go as quickly as possible to the finishing line, and stop at the finishing line. Okay? I don't want you to overshoot, okay? It's not like the regular race. I want you to smack and stop on the darn thing. What's your control strategy? Yeah, straight. But what do you do with your gas pedal? I understand that the steering is not the issue. Gas pedal. Full blast. Okay, you just hit it as hard as you can, assuming your tires don't touch so much. Okay, that works fine for the beginning. What do you do towards the end? Full blast. Brake. So that is essentially the idea of bang-bang control. So one bang is take maximum motor commands you can generate. And then when the right time comes, and that is now the magic of the race car driver, you hit the brakes like a crazy person, just the right way, so that you brake with maximum deceleration, stop on the line. So this is actually interesting. So the control policy for that is actually incredibly trivial. It's binary. It's just full blast or full blast off. That's why it's called bang bang. And there's actually many people sometimes, which is when you look at research paper, they create optimal control problems. They say, oh, I want to do something in minimum time or whatever. Minimum time problems are surprisingly simple, since what people say, all what you need is what is called the switching surface. This is the moment where you basically switch from one extreme of the motor command to the other extreme of the motor command. So there's the motor command policy over time here really looks just like full blast, full acceleration, all of that. That's it. And all what you care is this point of switching. So it's actually a very trivial motor control policy. It just has really one parameter which you have to optimize. And it's kind of important to know that when you see problems like this, they're much simpler to tackle than some complicated continuous time problems where you cannot do the switching, where the motor command permanently varies. So it's just a good thing to know. Bang-bang control is kind of the technical term people like to use. Other things is minimum motor command control. That's very simple. We basically take these are vectors, so we take a squared motor command, and we may put some metric in between. So R is a positive definite matrix, and, well, you can basically say R equals just the identity matrix if you want. That's super simple, like this. But you could also say it is like, let's make this my arm which is moving. And I say, okay, if I move my shoulder, that costs me a lot of money because I have to move a lot of inertia. So how about I put a big weight on that? So the shoulder is degree number 1. So I make this 100, and say my elbow costs me only 10. Losing the wrist is totally cheap. Moving the fingers is very cheap, and then losing the last segment of my pinky that cost me almost nothing. So that's actually a useful way of weighting things. But you also notice it's an arbitrary way of weighting things. Someone has to come up with weights. And you will actually see when you play with optimal control problems, these weights make a big difference how things actually come out and appear. And that gets us into this trouble in general with optimal control. We express our objective in some very strange parameter space. So here this matrix A, for instance. And you will see in a moment we put some state cost in there, and we get another matrix, which is the matrix Q, which says how much should I be penalized for being in a particular state, or something like that. These parameters are not easy to set. It's nice if you can do identity matrix or some simple rules. Often it's basically people tweak them so they get the behavior they want. Now you can also take very complicated terms. Any arbitrary nonlinear term in X and U and whatever you want. The issue is that if you do this, you will be seeing that you cannot solve that optimal control problem analytically anymore. You have to do a complete numerical solution. If it looks like this, it actually is very easy to solve. That's a quadratic cost criterion, and you will see in a second how this inserts into the equations, and it's very straightforward to work with. Let's see. You can actually do cooler things as well. So some people try to basically optimize additionally the parameters in Q and R. So this is ongoing research.
where you create a meta optimization problem and try to get rid of the open parameter settings. People dislike that. It works partially, it's interesting, but needs more work. So let me go into something which is really pretty, and that is essentially linear quadratic regulator control, which is a special case of optimal control, but this special case we do understand really well, and it works really well. Okay, what we're going to do now is you assume that we have a linear system. Xn plus 1 equals A, that's a constant matrix, plus Xn plus B un. Okay, straightforward. And we have that nice quadratic cost function, L equals X transpose Q, and it has to be indexed with I at time I, so L at time I, like this, plus U transpose B UI. Okay, got that. Now, it's kind of boring, it's a linear system, but linear systems are not necessarily bad, since you can take a nonlinear system and linearize it at every time step. And that's essentially what people do when they try to solve nonlinear optimization problems frequently. They simply say, okay, my real system is Xn equals of this type. And then at every time step, you do a linearization, which you know how to do with a Taylor series expansion. And that means at every time step, you get this particular system. If you do this, then A actually starts to depend on N as well, since it changes from time step to time step. But it's totally doable. And if you do that, you can basically solve nonlinear optimization problems with the same idea. Now, we are currently bound to having these quadratic functions here. That is important. So we can only be quadratic in the states and quadratic in the commands. We cannot do nonlinear terms in the ITLC, otherwise we can solve the problem. Okay, and you can think of this here, for instance, as a problem which is a set point problem. So you want, in its original form, when you just forget about it, these things depend on time. For instance, a typical problem that people have studied a lot is the kite pole problem. So what you have here is a toy problem, but it's kind of interesting. It is a cart with two wheels. On it is a balancing pole, which basically has a hinge here, maybe a little mass on top. And what your goal is to basically take this here to a particular goal point and keep it upright here, balance it. So it's like balancing a pole on a fingertip. It's the same idea. So this is why is this an interesting problem? Any idea? I don't have a stick here, unfortunately. What is interesting about the pole problem is, if I'm here in this position, okay, and I want to go over here and balance that pole over there, there is a very non-intuitive way how I have to do that. So let's do it the dumb way. Let's assume, so I'm here, I want to keep this upright, and I want to go over there. So I just create a PD controller to put me into that state. Okay, I could do that. Unfortunately, this is not going to work. Since basically when I start accelerating towards the goal, the pole will tilt backwards due to its inertial properties, and I will fall over, annoyingly. So what I actually have to do, interestingly, I first have to go backward, have the thing tilt forward, then I can move there, then catch the band and balance. So these systems are called non-minimal phase systems in the control language. But essentially, the idea is that in order to reach the goal, you have to go away from the goal first, which is weird. So just coding this with a simple PD controller will normally not work for you. At least you have to set the gains in a very special way to make it work. Let's put it this way. If you just play with gains, you will be very, very unhappy. But this is why this problem has been studied so much. It's a standard textbook example. It's cool. And people can basically solve it with LQR controls. This kind of optimization comes up with the right solution. Okay, so
Now, if you have a problem like this, then the easiest way is to basically find x relative to the goal. You basically say here, my x is relative to the goal, so I call this here x, which is essentially my current state minus the goal. So it's redefining. And what I want to do is I want to basically regulate the state x to become 0, and I want to use as small motor commands as possible in order to get there. Now you can also, again, a nice, why has it become a B? That's weird. It was meant to be an R. Again, now these values in the Q and R matrices become critically important. If you basically say, I put very big values into R, that means you want to have minimal motor commands. You will go very, very slowly in order to get there. If you put very big values into Q and keep R small, you will be very aggressively racing for the goal and try to stabilize there. And you will see there will be solutions which oscillate a lot initially and then come to rest, or some which goes beautifully smoothly there. So it's a little bit of a game. In MATLAB, there's a Simulink toy example where you can do pole balancing and see how this actually looks like. Good. So let's figure out what it takes to get the optimal solution for that. Brilliant. Cool. So we need to basically start with Bellman's principle of optimality and work our way through that. So we have J star equals argmin of L at time I plus J I plus 1 of xi plus 1. Is that the right way of writing it? Good. So, good. Few things to note in order to apply that. I can only do this math if I know xi plus 1 based on my current command and state. That means I need to have a model of the system. This is my model. These are my model equations. That allows me to predict xn plus 1 by choosing a state xn in un. It is very important that many of the optimal control approaches do need a model and work excessively with this model. And if this model is wrong, you get into trouble potentially. There are other methods which work without models, and that goes into the domain of reinforcement learning, but that's a totally different topic which goes much more into machine learning. Good. Now, if you have this, now you start just inserting stuff. So let me see. First of all, so basically L, we have this function, so we can just stuff all of this in here. So not so hard, and this is done here. And J, we basically can also expand xi plus 1 with our model knowledge and get this nice equation here. So not so bad. So this is now already a more structured equation since we put in the knowledge which we have. Now, given that we have a linear system, a linear controller will in the end actually do the trick. And the linear controller in this particular case, as shown here, is going to be that the optimal motor command x star, u star, at every moment I, is going to be minus k, some gain matrix, which changes over time, times xi. Okay? So that is something you can actually show that this is going to be the optimal solution. But for linear systems, you can also just assume that a linear controller will do the job, since a nonlinear system will not make much sense in this case. Now, if you buy that, then you can also basically see that the optimal cost to go is going to be a quadratic function in x. Now, why is that the case? So, we call basically the optimal cost to go Ji star to be xi transpose some p matrix xi. Why? Well, remember what we're doing is this kind of optimization problem, and we can start at the end. So here's the kind of goal state. And then we basically go one state backward. Now, from the goal state, if I basically just look at the cost for my last step, okay, then I just get something. I'm in this particular state here, xi. I'm going to go to xi plus 1 with some motor command ui. If I take the motor command ui to be a linear controller, I can plug this in here. So that means this term here, so ui transpose r ui is going to become xi transpose ki r ki xi. I'm just plugging this here in for you. That here is essentially some matrices multiplied to each other, which is p, and then we have state xi. So that basically gives you the idea that the cost is going to be, well, this cost term is actually going to be quadratic in x. And the first term is anyway quadratic in x. So that everything has to in the end always stay a quadratic term in x like this. So that gives us some knowledge about the structure of that kind of cost to go. It's a very simple, basically, quadratic term with a matrix P, which is kind of a positive definite matrix in this thing. Okay. And if we have that, then we can do all the beautiful math to get it going. So let's see how much you want to go through that. We have this. Rid of all of this. And we can just write this out one more time. J star now equals optimum here, arg min of xi transpose q xi plus ui transpose r ui plus j star at time step I plus 1 of our model. Okay. And now we can basically say, we can know this knowledge that this has to be a quadratic function in state. So we start replacing this term simply by saying, okay, my state is going to be axi plus b ui. Remember, this is nothing but xi plus 1. I put in my p term. It has to be index I plus 1, and then I get this has to be transposed, and I get a xi plus b ui again. So that was straightforward. And now, given that I have that and I want to optimize it or minimize that, I have to just take, okay, oopsie, dj star at time step I with respect to the current motor command u subsum I. And now you get, at this point, most likely the idea why I chose a quadratic optimization criterion. Then, if this in here, so now I basically have to take every derivative with respect to ui, and then I want to solve for ui afterwards. Now, as long as ui appears in those equations here in a quadratic term or in a linear term, I'm fine. That usually means if I basically take the derivative with respect to a quadratic term, I just get a ui which is left over. If I take the derivative with respect to a linear term, ui disappears entirely. If there were nonlinear terms in there, it would not disappear, and I would get nonlinear terms to work with, and most likely could not solve that in the end for ui. And that is my key problem. So quadratic terms allow me to basically put through the math analytically, and I get nice solutions. And that's essentially what you got to do. So fine, let's try this game. So if I take the derivative with respect to that, let's take the first term here. Derivative with respect to this, which with ui. Yay, it's nothing. There is no ui. I love that. So that goes away. Then this term is simple. This becomes essentially UI transpose times R, and I took the derivative back to this UI. There's another UI. God, there's so many UIs. Here's one too. Why did I ignore this? Well, I do a little trick. You know what I can do? I can take, these are all scalar terms, they're cost terms. So I can just take the transpose of it. Why not? What's the transpose of that? Well, very excitingly, this is exactly the same as it currently is. So let's call this here my underbar UI, and this here is my squiggle UI. And now my squiggle went here, and my underbar went there. So fine. So this means I can take derivative with respect to the other UI, and I get, this was my underbar, this is my squiggle. Now I essentially get this term again. So fine, it's just made as a calculus with matrices. So it's the same as when you take the derivative of u squared with respect to u, it's 2u. Not a big deal. The same happens with matrices. You can basically do this little trick as I showed you if you want to derive it. But in the end, all what you get is that you get 2 I times r. Good. Easy. Now, the next part is basically the stuff in here. So we have essentially multiple terms. You have to multiply this out, which is annoying. So these terms, get rid of this, is going to be xi. This is as a transpose, so I have to bring the transpose in. A transpose times pi plus 1. You see, this is kind of messy to write in the end. And multiplying this term, axi. This is one of the terms I have to consider. Then I have a term which is just quadratic again, which uses the 2 u's. So I get ui transpose b transpose pi plus 1 b ui, and then I get cross terms. So AP times this and BP times this. Okay, this is going to be XI A transpose. It's very easy to draw transposes at some point of life. Times BUI, and the other term is this one here. This is I plus 1 AXI. And for the same argument, this term and this term are identical since they're scalars. If you take the transpose of this, it becomes this term. P is going to be a symmetric matrix. Okay, I hope I did the same here. So fine, if you get this, you take derivatives. So this term, when you take the derivative with respect to u, is irrelevant, doesn't have a u. Lovely. Then this term is again a quadratic term, so that is straightforward. So we get another term plus 2, this term here, ui, the i's become up there, transpose times b transpose times pi plus 1 times b. I hope this is correct. We'll see this in a second. And we get one more term from this. So this is essentially, we can get rid of this term and just write a factor 2 in front of it. And we can take the derivative with respect to ui, which is back there. So this is going to be 2xi transpose, a transpose, pi plus 1, b. Okay. And this has to be equal to 0, all these terms together, of course, in order to find the optimum. So standard calculus. Fine. And now you can see, okay, I can solve that for ui's. They only appear linearly. The factor 2, given this has to be 0, you can get rid of. This is also nice. And now we basically have to pull ui out. That is hopefully, well, if you write this nicely, it's an ui transpose multiplying r plus b transpose pi plus 1 b This is this term. And we have this other term left. So this can be, if we basically we can write this then with a negative sign equals minus this term here, xi transpose a transpose pi plus 1. So it becomes annoying matrix algebra, to be quite honest, but it's not very complicated, it's just annoying. And now I can basically solve for ui by simply inverting this matrix and bringing it on the other side. And I also basically am a little bit annoyed with all these kind of transposes, so that I can just transpose everything away. So if I take the transpose of this expression, then all of us, what happens is that the sequence changes. So this is essentially what has happened here by now. And you get essentially that you have to invert this big matrix, which we have here, I transpose B transpose Pi plus B, and you have these terms here left, which are here. Just the sequence has changed because I took the transpose. It's B transpose Pi plus 1A, and then there's Xi. Cool. Now, all what I'm going to do now, I call everything which is multiplying Xi simply a gain matrix Ki. Since that's what it is, it's just a bunch of matrices multiplied with each other. It's not a big deal. And the other thing which is interesting, so you might want to look at this matrix here. So this has to be invertible. If this is not invertible, you get into trouble. So when would it not be invertible? Well, if B has some strange properties, that means it basically makes this here rank deficient, you can get into trouble. If R has some rank deficiency, that means it's not a full matrix, you could get into trouble. In the end, it matters whether the entire expression remains invertible or not. Okay? Good. Well, we have that. The good thing is now we basically computed the optimal gain. Is my computer working? Yeah. The optimal motor command based on a gain matrix at time step I. But it's a little bit of a cheat since we know almost everything. R, we made up. That's part of our cost function. B is part of our model, so we know that. And A is also part of our model. But Pi plus 1 is a little bit of a bastard, since that we don't know yet. But that gets us back to this picture that if I start basically at the goal and go backward, the last Pi plus 1 I would be able to know. So it essentially hints at that there is a backward sweep in a recursion which allows you to solve that. And we can now basically go and look at the update of the matrix P. I'm not sure whether I want to write this down entirely again. It's too much fun. So how do we do that? So we have now, again, our cost function inserted in the Bellman's optimality principle. We have the model inserted in Bellman's optimality principle. And what I'm going to do now is I know that I can solve the minimization problem by plugging in this control law which says ui equals minus k times xi. Okay? This control law I know is going to be optimal, and I know what k looks like. The way you just compute it is just not pretty. So fine. How about we basically, so that means I can drop that kind of minimization thing by just plugging in the control law. This is what happens here. ui gets replaced with k times xi, just transpose, so the sequence changes. The same here, we do the same with ui here, ui there. Okay, so that is basically now an equation which tells me that my optimal cost at time step I is somehow a function of all that mass and the optimal cost at time step I plus 1. Okay? The rest of the things we know, and we know that in K, we have somewhere that Pi plus 1 again. Good. And you can basically plug it all in. It's so much fun. So we try to actually pull out all the state xi and have all the matrices in the middle of the system. So it's basically you multiply this out, extract xi, multiply this out, extract xi, and you get a lot of terms, which is basically every term. Basically, what is important is that every term here is essentially quadratic in xi. Because this here xi multiplying xi, this here multiplying xi, all quadratic terms, so it means you can write some big matrix thing in the middle. And you know that this, so again, what you see is that the optimal cost to go is quadratic in xi. Here's the xi, there's the xi, and then unfortunate term in the middle is just big, but that's it. So we know that this term in the middle has to be pi, and it depends on pi plus 1. Cool. And now you have the recursion how to compute pi given your knowledge of pi plus 1, which is very nice. So if you start at the goal and compute trivially pi plus 1, you can basically compute the next pi based on your knowledge of the gains k and the system model and the cost function. So, fine. So that's essentially our solution to this entire problem. And what is important is actually this equation here is called the algebraic Riccati equation. This is an equation people have studied before. And it turns out that this equation, when you iterate it through time, iterates to a fixed point. That's actually very easy to see. And, well, easy to see. To prove it is a little bit more work. But the idea is, so this is called the Riccati equation. And these Riccati equations appear in optimal control all the time. Which says that pi equals some big stuff depending on pi plus 1 and all other terms which we know. And you can see whether this equation has a fixed point by simply saying, oh, does it converge at some point? So what's the equilibrium point? Equilibrium point analysis, you guys know. It's kind of the same idea. So let's assume at some point the darn thing converges. That means pi has to be equal pi plus 1 since it doesn't change anymore. Okay? And you can plug this in. And if you do this, then you can essentially figure out what are the gains at this converge stage. And you can also, what is the p at this converge stage. And what turns out in all these LQR problems is that you just sweep about 30, 40 steps backward and you figure out that your gains k converge and your matrix P converges the cost to go. And it's kind of interesting. That means essentially what people do, instead of basically looking at what is called a gain schedule, where you say, okay, I have a gain k at n minus 1, and then I have a gain k at n minus 2, and I go backwards. They just go directly to the converge gain k and only use that. They don't use that special gain schedule. The special gain schedule, if you change them, that is truly optimal for this kind of finite time horizon problem. But given that it converges so quickly, it is totally sufficient to work only with the converge gain k. And that essentially would correspond that you have an infinite horizon problem, that you basically assume you apply this forever after. Except that the time horizon, when it converges, that's 50 time steps usually. It's very little, so they kind of, after 50 time steps, the problem appears like an infinite horizon problem. And that's very convenient. So that's when you go into MATLAB, for instance, there is a beautiful little function which is called DLQR. It takes its argument, the A matrix, the B matrix, the Q matrix, and the R matrix, and it spits out the gain matrix. You can also get the P matrix if you want. Very, very simple. And the way this is computed is, well, MATLAB uses a special method how to compute it, but the simple way to compute it, you just basically take this Riccati equation, you make a first guess for pi plus 1. And from that, you can compute the gain. you update PI, then you basically, with this new PI, you compute the gains again. You update the next PI, and you just iterate this for 50 iterations, and you have a converged K, and you have a converged P, and you're done. And this is essentially what is spit out here, and that's what you apply to your control system afterwards. So very straightforward, very nice to work with. And that's essentially the whole idea of LQR control. Let me see. Is there anything which I forgot? No. It's very easy to implement, so you can do this yourself. MATLAB implements it in a kind of eigenvalue, eigenvector method. There's a different way how to solve that, except that it is more brittle. So MATLAB is more susceptible to some matrix inversions. I think when the A matrix is rank deficient, bothers MATLAB. If the A matrix is rank deficient, it does not bother if you just iterate the Riccati equation backwards. So that's kind of interesting. So that's a more robust way of doing it. It's just not as fast. It's just an iterative method. Okay, so that's essentially LQR control. Something which, once you basically implemented this function, how to solve it, it's really straightforward. It's just matrix algebra. Make sure you don't mess up the indices. Do your matrix algebra properly. If you would use a tool in C++ like Eigen, this is super fast coding. It's not a big deal. You just iterate to that. Yes.
So all of this is like offline algorithm. I mean, you compute it beforehand, right? Before you execute.
Good question. And the answer is yes. Most of the time, if you know your system and your cost function, you compute it offline, you get a gain matrix, and then you just work with the gain matrix K and apply it to your control system. Now, what people do some people do basically adaptive controller, learning controllers, where potentially the A changes, or you do a nonlinear optimization problem where the A changes over time. Since you don't know exactly which state you're in, so if you're a nonlinear system, you make a step forward, then you have to linearize at that new state, and you have to recompute the gain matrix K for that moment. So then you have to iterate. It's very easy. It's very fast. You know, on a modern computer, that's literally microseconds. There's no issue to iterate these things. It's a very nice, robust control method. It gives you gains, and you don't have to worry about twiddling gains yourself anymore. You do have, and this is very important, you do have to play with Q and R values. And you will see big differences in how you set them. And there's some intuition, and unfortunately, it's not fully automated at this moment of time.
The R is weights of the
commands. Yeah.
The Q is
weights of the state. Yes.
Like if we're in a robot, it means we want to like desired joint position or something for Q. For Q, that usually means. In the case where you want to go to a particular goal, is how far am I away from the goal? That is what basically the state would be, the difference to the goal, for instance. But you can reformulate it. All what it means is you're depending on state only. Last but not least, for continuous time systems, I mentioned that at the beginning, things change a little bit. You now write continuous equations, so you get x dot equals f of x and u. The cost function now becomes an integral over the cost. It's not a huge difference. You still have a terminal cost. And the Bellman's optimality principle becomes the Hamilton-Jacobi-Bellman equation, which looks like that. So it just becomes some differential stuff. It works in the end in exactly the same way as what you just saw before. You basically plug, if you do LQR in continuous time, you would plug in your cost function. You know your model, which is now this kind of continuous model. If it's linear, it's easy to solve. If it's not linear, you have to locally linearize at every time step, and you get the same solution with something which is the gains basically multiply the state x, and that's your motor command to get this linear gain system. Okay. People love that method. It's very important. Many people use it. It's incredibly robust. It's incredibly easy to design. MATLAB has beautiful tools to compute it. You don't even have to know anything about it. And even coding it yourself, if you see that Riccati equation, which just has to converge and get the gain, is trivial. It's really trivial. It's like 2 pages of code at most to do that. You can make it ugly and make it half a page of code. Nobody can read it, but it's good enough. All right. That's essentially for today. I will send you emails about the Now simulator in the next few hours and fix everything. All right, thank you.